You've seen how to find values for these two irrational numbers, e and pi, as the limits of two suitably chosen sequences. Unfortunately, those sequences converge rather slowly, so it's tedious to use them to evaluate e or pi to any great degree of accuracy. But fortunately, there are other methods for determining their values accurately. We'll be dealing with pi in the second analysis block. It's e that we want to concentrate on in this program. So what was the definition of e? In the last program, we defined e as the limit of this sequence, 1 plus 1 over n to the power n. Unfortunately, you have to take n to be at least 10 to the 6, even to achieve this degree of accuracy, 5 decimal places. In this program, you'll see that series give a much quicker way of calculating numbers like e. You'll also see how to use series to sketch the graph y equals e to the power x, the exponential function. So, what do we mean by a series? I'll introduce the notion of a series by way of an analogy, a growing snake. Let A1 be its length at the end of year 1. During year 2, it has extra growth A2, so that at the end of year 2, its overall length is A1 plus A2. During year 3, it has extra growth A3, so that at the end of year 3, its overall length is A1 plus A2 plus A3, and so on. The numbers A1, A2, A3, and so on form a sequence, and the actual length of the snake at the end of year n is the sum of the terms A1 plus A2 plus A3 up to plus AN. That's the sum of the first n terms, what we call the nth partial sum. The result of adding up infinitely many terms is what we call an infinite series, or just a series. Because the terms in the series are positive, its partial sums are increasing. That means that the sequence of partial sums will either tend to infinity, and we say that the series diverges, or it will tend to some given value, and we say that the series converges, and the limit of the sequence of partial sums is the sum of the series. It is convergent series that give us an effective way of calculating the value of e.
For simplicity, I'll work with series whose terms are positive. Then we can think of the terms as forming a positive sequence. Here's the first sequence, 1 over 2 to the n. And down here, I've represented the terms by strips of appropriate length. A1 is a half, A2 is a quarter, and A3 is an eighth, and so on. It's a geometric sequence, and when you add up the terms, you get a geometric series. In terms of the snake analogy, the annual growth each year is half the growth the previous year. Let's begin by adding up the first 3 terms. Here they are. And that summation can be expressed by this symbol, sigma, where this is a general term, and the sum starts from 1 and finishes after the 3rd term. When you add up the terms, you get partial sums. The first partial sum is just a half. The second is a half plus a quarter, that's 3/4. And the third is 7/8.
So on the number line, here is a half, the first term of the series. And the first partial sum is also a half. That's represented by S1. The second term is a quarter. So the second partial sum, S2, is 3/4. Here's the third term, an eighth. And so our third partial sum, S3, is 7/8.
But really what you want when you're working with series is to see whether you can add up all the terms like these. And that can be expressed like this, where the symbol for infinity is used here to indicate that you're adding up all the terms of the form 1 over 2 to the n, starting from n equals 1. but what happens on the number line when you add in more terms?
Well, if S3 is 7/8, then S4 is 15/16, and S5 is 31/32, and so on. The partial sums seem to be getting closer and closer to 1. It looks as if this series converges, and its sum is 1.
There's another way to look at it. This is a unit square. And I'm going to represent A1, which is a half, by this triangle. The bit of the square left is also equal to A1, and A2 is half of it. So all this is S2. The bit remaining is the same as A2, and A3 is half of this space. So this is S3. And so you go on. Each time the next term is half the remaining triangle. And continuing like this, you get very close to filling the unit square. This illustrates that the sum of these areas is 1. But how should we approach this analytically?
What you have to do is to see whether the sequence of partial sums converges. Well, S1 is a half, which, as Ian noticed, I can think of as 1 minus a half. And S2 is 3/4, which I can think of as 1 minus a quarter. Then S3 is 7/8, or 1 minus an eighth. So what is the formula for the nth partial sum? In fact, Sn is 1 minus 1 over 2 to the power n. So, as n tends to infinity, the partial sums Sn do tend to 1, because 1 over 2 to the n is a null sequence. So, this series is convergent. It makes sense to say that the sum of this infinite series is 1.
Now, not all series are convergent. For example, if you start with the constant sequence, an is equal to 1, then that gives you a rather trivial example of a divergent series. The successive partial sums are 1, 2, 3, and so on. In general, the nth partial sum is n, which tends to infinity as n increases. The partial sums diverge, and so the series itself diverges. This series has no chance of converging because the partial sums are increasing by 1 each time. Now, what was the corresponding situation for the geometric series which did converge? Well, successive partial sums tended to a limit, and so the individual terms, the difference of successive partial sums, tended to 0. So let's look next at this sequence, 1 over n squared, where the terms do tend to 0, so that this series does have a chance of converging.
For the series sigma 1 over n squared, the first partial sum is 1, the second partial sum is 1 plus 1 over 2 squared, the third is 1 plus 1 over 2 squared plus 1 over 3 squared, and the nth, Sn, is 1 plus 1 over 2 squared plus 1 over 3 squared, and so on up to plus 1 over n squared. Obviously, the partial sums are increasing. So, by the monotone convergence theorem, either they tend to infinity, or they tend to a finite limit, depending on whether they are bounded above or not. To see whether the Sn are bounded, you can use an inequality first noticed by the Swiss mathematician Euler. Now, it's obvious that for any integer n greater than 1, that n squared is greater than or equal to n times n minus 1. So, taking the reciprocal of this inequality, you get that 1 over n squared is less than or equal to 1 over n times n minus 1. And as you'll see, it's more convenient to write the right-hand side as a difference of two fractions, 1 over n minus 1 minus 1 over n, when you use a bound of this sort for each term in the series. So first, putting n equals 2 in Euler's inequality, you see that 1 over 2 squared is less than or equal to 1 over 1 minus 1 over 2. So S2 also satisfies this inequality. And what do you get putting n equals 3? A third squared is less than or equal to 1 over 2 minus 1 over 3. And so similarly, S3 satisfies this inequality. And here's what you get for Sn. It's less than or equal to this expression. Now you can use telescopic cancellation to simplify this expression. The minus half in this bracket cancels with the plus a half in the next bracket. The minus a third here cancels with the plus a third in the next bracket, and so on. And finally, the minus 1 over n minus 1, which would be in the second last bracket, cancels with the plus 1 over n minus 1 here. And what you're left with are minus 1 over n still at the end, and the terms 1 plus 1 at the beginning. So Sn is less than or equal to 2 minus 1 over n, so that every Sn is less than or equal to 2. The sequence of partial sums is increasing, and is bounded above, so it does tend to a limit. And that means that the series is convergent. And actually, since all the Sns are less than or equal to 2, it follows that the sum of the series is also less than or equal to 2. In fact, Euler was able to show that the sum of this series is pi squared over 6, or about 1 2/3. Now, you've seen that if a series converges, then the individual terms in the series must tend to 0. That is, they must form a null sequence. Well, here are 3 of our basic null sequences. First, the sequence c to the n. You've seen that the series sigma half to the n converges. Its terms are of the form c to the n with c equals a half. And you've seen that the series sigma 1 over n squared converges. Its terms are of the form 1 over n to the p with p equal to 2. They form a null sequence as well. Those examples illustrated the fact that if a series converges, then its terms form a null sequence. But the converse doesn't hold. It's not true that if the terms of a series form a null sequence, then the series necessarily converges. Ian?
Let's consider the sequence 1 over n. That is a null sequence, and it's very tempting to think that it would give rise to a convergent series. But sigma 1 over n is divergent. Let's have a look at it. Here are the first, second, third, and fourth terms from the sequence. And if I put a quarter up here, you can see that these two together come to more than a half. So the partial sum S4 is 1 plus a half plus a bit more than a half. That's more than 2. Now look at the next 4 terms. As you can see, these give more than a half as well. So the partial sum S8 is going to be the sum of all these terms. 1, 1 and a half, more than 2, more than 2 and a half. So that's S1 up to S8. And if I continue to add groups of terms like this, the next 8, then the next 16, and so on, each one double the size of the previous one, then each group contributes more than a half to the sum.
Here then is what we know about the series sigma 1 over n. Its first partial sum S1 is exactly 1. Its second partial sum is exactly 1 plus a half. And as Ian showed, S4 is greater than or equal to 1 plus 2 times a half, and S8 is greater than or equal to 1 plus 3 times a half. There's a general pattern building up. Here's the second power of 2, and a 2 here. The third power of 2, and a 3 here. So in general, the 2 to the case partial sum of sigma 1 over n is greater than or equal to 1 plus k times a half. And as k gets larger, this lower estimate for partial sums tends to infinity. So the partial sums themselves must tend to infinity. So the series sigma 1 over n must diverge. And that immediately shows that the converse here doesn't hold. All you can assert is that if a series converges, then its terms form a null sequence. Now, the last sequence here, c to the n over n factorial, is the key to the new definition of E promised at the beginning of the program. So let's look first at the case c equals 1. That's the null sequence 1 over n factorial. Terms of that type give the infinite series sigma 1 over n factorial.
Here are two results from last week's program. The first one defines E as the limit of an infinite sequence, and the second is an inequality which follows from the binomial theorem. Now this inequality remains true if I add some extra things on the right. For example, making this an infinite series. Now, this much is sigma 1 over n factorial from 1 to infinity. But naught factorial is defined to be 1, so I can think of this 1 as 1 over naught factorial. Then this is equal to sigma 1 over n factorial summed from naught to infinity. Now if this infinite series is convergent, it will give us a number, an upper bound for the binomial expression. In which case, the limit inequality rule gives us the result that this is an upper bound for E as well. In fact, a much stronger result is true, as you'll see in the unit. E is equal to this infinite series. But first, let's justify that this series is convergent.
To show that the series sigma 1 over n factorial converges, you can use many of the ideas that we used to show that the series sigma 1 over n squared converges. Because Euler's inequality that 1 over n squared is less than or equal to 1 over n minus 1 minus 1 over n holds also for 1 over n factorial. You see, n factorial is greater than or equal to n times n minus 1, because n factorial is just n times n minus 1 times some more integers. So, taking reciprocals of this inequality just as before, you get that 1 over n factorial is less than or equal to 1 over n minus 1 minus 1 over n. So, all of this working for sigma 1 over n squared will still hold for the series sigma 1 over n factorial. So, sigma 1 over n factorial from n equals 1 to infinity converges to some number less than or equal to 2. And that means that when you add in the extra term 1 over 0 factorial at the beginning, that sigma 1 over n factorial, summed from n equals 0 to infinity, converges to some number less than or equal to this 2 plus the extra 1. That's 3. Because this series converges, you can use it as an alternative definition of the number E. You can define E either as the limit of the sequence 1 plus 1 over n to the n, or as the sum of this series. For numerical calculation, the series is very much better than the sequence. For example, to calculate E to 5 decimal places, you need to only add up the first 8 terms in the series. Remember that in the last program we modified this definition of E to define e to the x as the limit of the sequence 1 plus x over n to the n. And you can modify our series definition of E to show also that e to the x is sigma x to the n over n factorial.
So let's look at this series, sigma x to the n over n factorial. Series like this, involving powers of x, are called power series. If you give x the value c, the terms of this power series are just the members of the standard null sequence c to the n over n factorial. I've assumed that the series is convergent and plotted some of the values. But even to get an indication of the graph, I should have to plot many more values. It would be easier to think of sigma x to the n over n factorial as a sum of functions, and add up the terms as graphs. Then I can check whether the final graph is that of e to the x. The first four individual terms of this sum of functions are x maps to 1, x maps to x maps to x squared over 2 factorial, and x maps to x cubed over 3 factorial. This is the graph of x maps to 1, this is x maps to x, this is x maps to x squared over 2 factorial, and this is x maps to x cubed over 3 factorial. Let's see how the partial sum functions build up. Starting with the first partial sum function, which is the initial function x maps to 1. To obtain the second partial sum function, S2, you have to add in the next term, x maps to x. That's going to give a combined function greater than 1 for positive x, and less than 1 for negative x. So this is S2. Now for the third partial sum. That means adding in x maps to x squared over 2 factorial. This function is positive except at the origin. So to the right of the origin, the combined function S3 will have larger values. And to the left of the origin, the graph will be raised up as well. So this is S3. Now for the next partial sum. You add in x maps to x cubed over 3 factorial. This makes the combined function steeper to the right, but to the left of the origin, these negative values will bring the graph down again. So this is S4. And continuing this process, here are the next partial sum functions. S5, S6, S7, S8, and so on. And in the limit, you get this graph. Certainly it looks like the graph of e to the x. It does pass through the point 0, 1, and if it is e to the x, then the gradient at any point must be equal to the function value. Let's look at that. Here's the tangent at 1. Now the gradient of the tangent is given by the height, that's the function value, divided by the base length. So for any point on the graph of e to the x, you'd expect the base length of this triangle to be 1, because that would mean that the gradient is always numerically equal to the height of the triangle, which is the function value. Watch what happens as the tangent moves. The base length does stay of length 1. So this curve is the graph of e to the x, and e to the x is the series sigma x to the n over n factorial.